Goal of this video will be to get some practice on continuity, on finding continuity of functions, and within that periphery we will solve NCERT class 12 exercise 5.1, and let's begin with the first problem. So the first problem says prove that the function f of x equals 5x minus 3 is continuous at x equals 0, x equals negative 3, and x equals 5. So we will follow, in this entire exercise, we will follow the same one rule. We have to just prove that limit as x goes to a of f of x equals f of a. And then that would guarantee that both of these quantities exist, f of a and f of x exist, and they have to be equal. That's the single equation that we have to practice throughout this exercise. So prove that the function f of x equals 5x minus 3. First, let's do it at x equals 0. So at x equals 0, limit as x goes to 0 of 5x minus 3. That's because since 5x minus 3 is defined at x equals 0, you just do 5 times 0 minus 3, and that's negative 3. And f of 0, that is f of 5x minus 3, is also equal to negative 3. So the function is continuous at x equals 0. I'll leave x equals negative 3 as a practice. Let's do x equals 5. For x equals 5, we have limit as x goes to 5 of 5x minus 3. If you put in x equals 5 here, you get a valid number, and that's equal to 22. And since that's not an indeterminate number, you can just write that this limit exists. And similarly, you can say f of 5 is equal to 22. So they both are again equal, and the function is continuous at x equals 5. One more thing I want to point out, that 5x minus 3 is a straight line. If you go on and you draw the graph, it would look something like this. There would be minus 3 here. This graph would have a slope of 5. So a straight line is always continuous. There are no breaks in a straight line. So let's move on to problem number 2. So examine the continuity of the function f of x equals 2x squared minus 1 at x equals 3. And you can do the same thing here as well. So limit as x tends to 3 of 2x squared minus 1. If you put in x equals 3 here, you would get 2 times 3 squared minus 1, and that's equal to 18 minus 1, that's 17. And f of 3 is again the same thing, it's again equal to 17. So the function f of x equals 2x squared minus 1 is continuous at x equals 3. Let's do the third problem. Let's clear up some space for the third problem here. So the third problem asks for at which points, it indirectly asks at which points is the function, are the four functions given as subparts continuous. And so let's examine them. Let's figure out what happens for these four functions. So I will do the last two functions, and the other two are also similar, so I'll do C and D. So let's start with the first. So x squared minus 25 over x plus 5, and x is not equal to negative 5. So if you see this function is equal to x minus 5 if x is not equal to negative 5. If x is not equal to negative 5, if x is equal to negative 5, then you get a 0 by 0 expression, and it doesn't make any sense. However, still the limit would exist, and this function is continuous at all points. This function right here, the original function, is continuous at all points except x equals negative 5. However, x equals negative 5 is already excluded from the quotient, so we don't need to worry about that. Let's try part D. So in part D, you have the absolute value of x minus 5. Now, if you plot this function, let's try graphing here. If you plot this function, so this is the y-axis, this is the f of x axis, this is the x-axis, and if you put in x equals 5, the value of y is mod 0, that's 0. If you put in x equals 6, so 6 minus 5 is 1. So, and if you put 4 minus 5 is mod of negative 1, and that's also equal to 1. Mod just removes the negative sign that you have. And so, as you increase the numbers in x, you just get an increasing value of y, and similarly, whatever values, positive values you get here by progressing in the right of x-axis, you also get the same values as you progress to the left of the x-axis. So notice this function wouldn't have any breaks. There is only one point of interest that might be the place where the function is not continuous. However, still there are no breaks in the function. This function would not be differentiable at this point, but it is continuous. So this is continuous throughout. Okay, let's move on to the next problem. So in the next problem it says prove that f of x equals x to the power n is continuous at x equals n, where n is a positive integer. So what that means is you need to find limit as x tends to n of x to the power n, and we have talked about this, that a polynomial function is always well defined at all values that you put in, and this is a polynomial function. This is where n is a positive integer. So this is a monomial term, and so it's just equal to n to the power n. You just put instead of x, you put n, and you get the answer. And similarly, f of n is also equal to n to the power n. So since both of these are equal, the function is again continuous. You could have taken another approach. You'd have said, let's graph the function, and the graph would have looked something like this, and some approximation to this, and you would have said that this function has no breaks. So at, let's say this is n, it would have assumed the value n to the power n, and it's continuous. There are no breaks in this function near that region. Let's move on to the next one. So problem number 5 says is the function f defined by the following. This is a piecewise defined function, continuous at x equals 0, x equals 1, or x equals 2. So let's try the problem. So a nice way to start with problems like this would be to visualize what it looks like. So let's try drawing the graph of this function. So if x is less than or equal to 1, so if you put x equals 1, you get y f of x also to be equal to 1. If you put x equals 0, 0 is less than 1, it's less than equal to 1, so you again get the value of x, and you write that here. And notice once you have plotted these 2 points, x is a straight line, so you can just do that for the rest of the numbers below 1. For numbers above 1, so let's say you put in x equals 2, then 2 is greater than 1, so you have to take this part of the function. So in this case, let's say 5 lies here, and even a number not only 2, and a number 1.000001 is also greater than 1. So this also has its f value, f of 1.00000001 is also equal to 5. So the function for any values of x greater than 5, for any values of x greater than 1, have the value 5. And so you can clearly see that there is a break within the graph, and the graph is discontinuous. To prove that analytically, so let's start with x equals 0. By the way, this discontinuity is at x equals 1, not everywhere. So at x equals 0, limit as x goes to 0 of f of x is just equal to 0, right? And f of 0 is also equal to 0. But at x equals 1, the limit as x equals 0 of f of x does not exist. Does not exist. Why? Because if you approach 1 from the left hand side, so you approach 1 like this, then the value get increasingly closer to 1. But if you approach x from the right hand side, that is limit as x tends to 1 plus, the values of f of x get closer and closer and stay equal to 5. And since the left hand and the right hand limit are not equal, the limit, the double-sided limit, just doesn't exist. So if the limit does not exist, there is no point in checking f of 1. Even if it exists, there is no question of this being continuous at x equals 1. If you have x equals 2, by the way, so at x equals 2, if you approach, let's say x equals 2 lies here, so if you approach x equals 2 from this side, from the right hand side, then you get closer to the value of 5. If you approach x equals 2 from the left hand side, then the values get closer to 5 again. And if you are exactly at x equals 2, you are still at the value 5. So since the left hand side, the right hand side limit, and the value of the expression are equal to 5, the function is continuous at x equals 2. Let's continue talking about limits. Find all points of discontinuity of f where f is defined by the following functions. So let's take one of these functions, and the rest you can do as sort of an exercise. So let's take problem number 11. So f of x equals x cubed minus 3 if x is less than or equal to 2, and x squared plus 1 if x is greater than 2. So now notice that x squared plus 1 and x cubed minus 3 are well-defined polynomials. So they are continuous. However, these functions are not for the entire domain of f. They are piecewise. For x less than 2, this function x cubed minus 3 exists, but for x greater than 2, you have to take into account x squared plus 1. So what that means is the only point of discontinuity that can be there in this case is if x equals 2, and we have not still verified that, so let's do it. So limit as x approaches 2 from the left hand side. So that means when x is a tiny beanie smaller than 2, so we will take this expression right now, of f of x is just same as writing limit as x tends to 2 from the left hand side. F of x is same as writing x cubed minus 3, since we are taking x to be smaller than 2 in this case. If you put in x equals 2 now, it's 8 minus 3 is equal to 5. And if you do the same of limit as x tends to 2 from the right hand side of f of x, it's the same as writing the limit for this expression, x squared plus 1. Why? Since we are assuming that we are approaching from the right hand side, so we have a number that's a little bit bigger than 2. And if you put in 2 here, you get 4 plus 1, and that's equal to 5. So the limits are equal, so the limit exists, and the limit as x tends to 2 from both of the sides is equal to 5. If you now look at f of 2, so f of 2 means x equals 2. Now x equals 2 means you put in 2 at this expression, so 2 cubed minus 3, and that's equal to 8 minus 3, and that's equal to 5. So now you have that the limit as x tends to 2 of f of x is equal to f of 2, and so the function f of x is also continuous at x equals 2. For all other values of x, this function must be continuous because they are just polynomials then, which are always continuous. So the function is entirely continuous, though in some cases, in some instances, for example, this function right here, the function in part 12, is discontinuous at 1, discontinuous at 1, at x equals 1, because if you put in x a little bit smaller, the limit if x approaches 1 from the left hand side, that is, it's smaller than 1, then you get x to the power 10 minus 1. That's the one we have to take if x is less than equal to 1, and that's equal to 0. 1 to the power 10 minus 1 is equal to 0. And limit if x tends to 1 from the positive side of x squared. Now you're taking x squared because you're taking x to be more than 1. In this case, that would be equal to 1, and these are not equal. So the limit does not exist, and the function is discontinuous at x equals 1. You can try on the other problems in this list, and certainly this problem would be a lot more fun to do because there are 2 points where the function can be discontinuous. Let's move on forward. Let's think about some more problems. So the problem is the function defined by f of x equals x plus 5 if x is less than equal to 1, and x minus 5 if x is more than 1, a continuous function? So again, x plus 5 and x minus 5 are both polynomials. And polynomials are continuous everywhere in every number you put in. So the only point of discontinuity of the entire function f of x could happen if x is equal to 1. Because for all other values of x, you get a nice polynomial expression, and you don't need to worry about that. So you can check at x equals 1. At x equals 1, you have limit as x tends to 1 from the left hand side of f of x, and that's just equivalent to taking x plus 5, because then x, we are taking that x is smaller than 1, we are taking x from the left hand side. So that would be equivalent to saying limit as x tends to 1 for x plus 5, and that would be 1 plus 5, and that's just 6. If you approach from the right hand side, then limit of f of x as x approaches from the right hand side is equivalent to writing limit as x approaches 1 from the right hand side for x minus 5, because approaching from the right hand side means that x is a bit greater than 1. So x minus 5, and so 1 minus 5, it's equal to negative 4. Since these two are not equal, the limit as x tends to 1 of f of x does not exist. And if the limit does not exist, the function is not continuous at x equals 1. And if it's not continuous at x equals 1, it's not a completely continuous function. It's continuous at all points except x equals 1.